Hello, everyone. Welcome to the noon session. We are going to have in this session 3 talks. Throughout the talk, you can feel free to drop your question on the Zoom chat box. And for the first talk today, we are very happy to have Uri Zwick from Tel Aviv University, who is going to tell us about improved KSAT algorithms. Go ahead, Uri.
Okay, thanks a lot, Mirav. I would like, of course, to thank the organizer for giving me the opportunity to give this lecture here. I'm very excited. I'm going to tell you about improved KSAT algorithms using biased PPSZ. PPSZ stands for Paturi, Pudlak, Sachs, and Zain, that device the algorithm will be improving on. This is joint work with Thomas Hansen, Chaim Kaplan, and Or Zamir. Or is a PhD student of Chaim and I. He's now finishing, and he, of course, did most of this work. Okay, let's start with a very brief reminder of the 3-SAT problem. The input is composed of a collection of clauses. Each clause is a conjunction of 3 literals. Each literal is a variable or its negation. And the question, of course, is there a 0-1 satisfying assignment? Can we assign each variable a Boolean value such that all the clauses would be satisfied? This is, of course, the most famous NP-complete problem, so we cannot expect to solve it in polynomial time. But the question is, how well can we do? The naive algorithm simply enumerates over all 2 to the n truth assignments, and the running time, of course, is O star of 2 to the n. And the question is, can we do better than that? So there's a long line of works, and this is a very selective bibliography, but I'll just mention things that are sort of relevant to what we'll be talking about. All running times are, of course, exponentials. So when we talk about KSAT, the running time would be of the form C sub k to the n. So I'll only state the results for the constant C sub k. Schoening devised a very nice randomized algorithm based on a random walk, which achieved the following results. When k is 3, the running time, so the base of the exponent is 4/3, about 1.334. And for general k, the base is 2 minus 2 over k. This was improved for sufficiently large values of k by Paturi, Pudlak, and Zain that gave the following results. And soon afterwards, together with Sachs, they gave the following bounds for 3-SAT, the base of the exponent was 1.308. And for general k, this is the asymptotics. What we do here is we slightly improve on the PPSZ algorithm. For k equals 3, we changed the 3rd digit from 8 to 7. Unfortunately, for general k, we still get the same asymptotic behavior. We just managed to lower the base by some epsilon k, by positive epsilon k. Okay, of course, you should mention that the exponential time hypothesis states that C3 is greater than 1. The strong exponential time hypothesis states that the limit of Ck as k tends to infinity is 2. Okay, but still the question remains, what are the best constants that we can obtain? Okay, I'll spend quite some time explaining the PPSZ algorithm because our result builds on top of it, and without understanding PPSZ, we will not be able to understand our algorithm. And I think it's also interesting in its own right. It's a beautiful algorithm. So the initial step is to make the following assumption. Let's suppose that we only want to solve instances of KSAT for which we know that there is only a unique satisfying assignment. Okay, let's see what we can do then, and then see how we can extend it to cover the general case. Okay. So initially, the bounds that appear in the previous table were only under this assumption. Only later, Hartley was actually able to show that all the bounds that PPSZ proved under the uniqueness assumption actually apply without the uniqueness assumption. Hartley was also able to obtain a tiny improvement for k equals 3. By tiny, I really mean tiny, so he was able to reduce the base by 10 to the minus 24. Still, it's an interesting result because it shows that PPSZ is not optimal. However, he was only able to do that for k equals 3. His techniques break down when k is greater than 3. Okay, another related result, Scheder and Steinberger proved that if you're able to improve over PPSZ for unique KSAT, then you immediately get an improvement for KSAT, possibly a smaller improvement, but in order to improve on PPSZ, it's enough to improve on PPSZ for unique KSAT, and that's what we will be doing. Okay, so what are our results? We present a biased version of PPSZ. We improve on PPSZ for every k, which is at least 3. We get a noticeable improvement. The improvement is not by 10 to the minus 24, it's more like 10 to the minus 4, 10 to the minus 5, and we are lucky that we're actually changing the third digit after the decimal point. We get an even larger improvement for a variant of the satisfiability problem called not all equal SAT, which I'll mention in a while. For not all equal 3 SAT, we get a more noticeable improvement. And not all equal 3 SAT would actually be a nice playground to explain our results, because it's a very natural setting, and well, we'll hear about it in a minute. I'll try to convince you that the biased PPSZ is a very natural approach, which may hopefully lead to further improvements. Unfortunately, there are some not simple technical details in proving that this technique actually works. So of course, I'll only be able to give you the highlights. Okay, one important notion which used by the PPSZ algorithm is the notion of bounded implication. Let phi be a KSAT formula on n variables, and let d, which can be a function of n with some parameter. Now, we say that the variable x is d implied by phi if and only if there is a subset, phi prime, of at most d clauses, such that in all the satisfying assignments of phi prime, x is assigned the same value, either 0 or 1. Note, by the way, that if phi has a unique satisfying assignment, then every variable is implied by the whole of phi. But we are interested in implications by small collections of clauses. Why is this a useful notion? Because we can efficiently check it. As long as D is not too large, we can simply enumerate over all subsets of D clauses, and for each such subset, we can enumerate over all possible assignments of the variables appearing in these clauses and see whether in all these satisfying assignment, X gets the same value or not. Okay, so that's the notion of the bounded implication. I actually note that the use of bounded implication was actually suggested by Hartley in their original paper. PPSZ actually uses a stronger notion, which is bounded resolution, but we don't need it in our work in this book. Okay, so what is the PPSZ algorithm? A very nice and simple algorithm. Choose a random permutation pi of the variables of the formula. Now, go over the variables one by one in the order in which they appear in pi. And now, for each variable, if it is implied, if it is de-implied by the formula, then, of course, we know which value we should assign to xi. If not, simply guess it randomly with equal probabilities and independently of all previous choices. Now, once we set the value of xi, we can eliminate xi from the formula in the natural way. Of course, if a clause in which the literal corresponding to xi evaluates to true, we can remove that clause. Otherwise, we can remove the appearance of that variable in the clause. Okay, that's the whole algorithm. Note that there's no backtracking. We do that. We may get stuck at some stage. For example, it may be that both xi and not xi are being implied. Okay, in that case, we can just stop. But we just go on until the very end or until we discover a contradiction. And then we check whether the assignment we constructed is a satisfied assignment. If so, we're very happy. We solved the problem. Unfortunately, if it's not a satisfying assignment, we just repeat. And of course, if we do that a certain number of times and still haven't found a satisfying assignment, we give up and we say that the formula is not satisfiable. We may be wrong, of course. It's a randomized algorithm with one-sided. Okay, what is the biased PPSZ algorithm? It's very similar. I will not restate the first three statements, the first three operations. Now, the change is what happens if xi is not implied. Okay, what we do then, we don't guess xi uniformly. We somehow compute a bias, beta i, and we guess xi with the bias bi. So with probability beta i, we set xi to 1. With probability 1 minus beta i, we set xi to 0. Again, independent of all previous choices, and then again we eliminate all occurrences of xi and not xi from the formula. Okay, that's the whole algorithm. I hope you agree that it's a very simple and natural change. Of course, the whole question is, where do we get these biases? That's what I'll try to explain in the rest of the talk. So how do we get these biases, and why are there always good biases to utilize? Okay, so we need to start with a high-level analysis of PPSZ. For a given permutation pi, let us denote by g of pi the number of guessed variables in a successful run of the algorithm. Okay, note that what we assume that if we get to a variable and we need to guess it, we guess it correctly. Okay, otherwise, the minute we make one incorrect guess, the algorithm failed. So we condition on making the right guesses. Now, note that for a given permutation pi, this is not a random variable. This is a fixed number. Now, assume that we can actually bound the expected number of variables that we need to guess. Suppose that we can prove that the expectation of g of pi is at most 1 minus mu times n, where mu is some constant. Then, what is the success probability of one iteration of the algorithm? It's actually the expectation of 2 to the minus g of pi. Okay, now, conveniently, we can use Jensen's inequality, and we get that this probability is lower bounded by 2 to the minus the expectation of g pi, which is good because we assume that we have an upper bound on this expectation. So we get a lower bound on the success probability of the algorithm, which is 2 to the minus 1 minus mu times n. So the beautiful thing is that even though the algorithm, there may be a lot of dependencies in which variables are guessed, in order to get a lower bound on success probability, all we need to do is bound the expected number of variables that we need to guess. And this is very, very useful. This will also carry through to the analysis of biased PPSZ. Now, if a variable is not guessed, we say that it is forced, right? Or, okay. One other useful notion that I have to introduce is, instead of choosing the random permutation, we actually do that indirectly. We choose a random arrival times for all the variables, and we get the permutation by sorting the arrival times. So for each variable x, we let sigma x be a uniformly random number from 0, 1, independent of all the other variables. We refer to sigma x as the arrival time of x, and we obtain the permutation pi by sorting sigma. Now, of course, the permutation pi we obtain is completely random. The nice property of the arrival times, they are completely independent. In a permutation, the position of two variables are not completely independent. This messes up the analysis a little bit. So it's convenient to work with arrival times rather than a permutation. Okay, another very important concept is the concept of a critical clause. Remember that we assume that our input formula has a unique satisfying assignment. Under this assumption, every variable has a critical clause. What is a critical clause? It's a clause in which the literal of x is the only literal that evaluates to 1, to true, under the unique satisfying assignment. And it's easy to see that uniqueness implies that every variable has at least one critical clause, because otherwise we can flip the value of x in what we thought was the unique satisfying assignment and get another satisfying assignment. So this contradicts the uniqueness. Okay, so each variable has a critical clause. This is exactly where the uniqueness assumptions comes handy. Now, the next simple observation is that if the variable x is the last variable to arrive in one of its critical clauses, then x is forced, okay? Because we are essentially left with a unit clause after we removed all the variables that appeared before x in the formula. So x is forced, x is implied, even just by one clause. Okay, this leads us to the next concept of forcing probabilities. So we are delving deeper into the analysis of PPSZ. Let us denote by Q of P, and there actually are two other parameters that I'll neglect. D is how many clauses, the size of the implications we are allowing, and K is the K from the K-sat. I will mostly, if I don't specify K, I assume that K is 3. So let Q of P be a lower bound on the probability that a variable, an arbitrary variable, is forced, given that it arrives at time P. And in what I'm saying, I'm assuming that D is little omega of 1. So D tends to infinity as N tends to infinity. That would be enough. Okay, the existence of a critical clause immediately gives us the following very naive bound. This is exactly the observation I made in the previous slide. If the variable x appears at time p, the probability that the other k minus 1 variables in its critical clause appear before x is exactly p to the k minus 1. And if that happens, then x is forced even by just one clause. So that's actually the complete analysis of PPSZ. Now, PPSZ went further, and they were able to show that the forcing probabilities actually satisfy the following equation. Now, I see that I'm running a little bit behind schedule, so there's a very intuitive argument why this equality or almost equality holds, but I guess I'll have to skip it. The bottom line is that when Q equals 3, we get that the forcing probability essentially satisfy the following, are expressed essentially by the following formula. And the thing to note is that when P is small, the forcing probability is roughly P squared. It grows rapidly like a quadratic, but when P is 1/2, the forcing probability actually gets to 1. So if a variable appears after time 1/2, the probability almost 1, it actually will be forced. Okay, so the full analysis of PPSZ is the following. So what's the probability that a variable x is forced? We just need to condition on its arrival time. right? We already said that if it arrives after time 1/2, then it's forced with probability 1. Otherwise, we need to compute this integral, and doing that, we get the following expression, and this gives us the success probability of 1.308 to the minus n. Okay, so of course we need to repeat it 1.308 to the n times to get a constant success probability if the formula is satisfiable. Okay, now note that biased cases do not change the forcing probabilities. That's an important observation. Okay, finally, biased PPSZ. So when should we guess with bias? How should we treat the bias? Why does it help? So as I said, let's consider a very special case, a toy problem, not all equal 3-SAT. Okay, not all equal 3-SAT is a variant of 3-SAT in which in each clause we want each clause to have both a 1 and a 0. Okay, the question again, is there a 0-1 satisfying assignment? It's still an NP-complete problem. Now, actually, it's a subproblem of 3-SAT because if we have a clause, a not all equal 3-SAT clause, we can actually convert it into 2 3-SAT clauses. But we want among x1, x2, and not x3, we want at least one literal to get the value 1. This is exactly this condition. And we want exactly at least one of them to get the value 0, so it's exactly this condition. So not all equal 3-SAT is a subproblem of 3-SAT. No faster algorithms were known for not all equal 3-SAT. Okay, the bias arises very naturally in not all equal 3-SAT. Okay, suppose that we have a not all equal 3-SAT clause. Now, these are the possible truth assignments. So 2 of the variables get the value A, and the other variable literal get the value not A. So from that, we immediately see that in any not all equal 3-SAT clause, if we choose 2 random literals that appear in the clause, then they are different with probability exactly 2/3. Okay, that's nice. Why is that nice? So suppose that we look at the 3 variables of such a clause, and we look at the order in which they appear in our random permutation. Now, if the second variable to appear is not forced, then clearly we should not guess it uniformly. We should guess it with a bias towards the negation of the first variable that appeared in the clause because of this condition in the box. Okay? Now, this is true in general, but clearly there's quotes because there are some small print. Why? We need to condition on x2 not being forced. So it's true that x2 with probability 2/3 would be different from x1, but we're only gaining from cases in which we're actually having to guess x2. If x2 is forced, we don't gain anything. So we need to show that we actually gain something. That's one difficulty. The other difficulty is that what happens if x2 is actually a second in several clauses? Okay, then which clause do we use? So this seems to be a good thing, but actually it complicates the analysis, so we have to also take care of that. But let me just very quickly explain the general idea of solving the main difficulty. How do we get rid of or control this conditioning? So the most important observation here is that if x appears early enough, so if sigma of x is p, where p is less than some parameter t, then the probability that x appears second, which is about 2p, is much larger than the lower bound that we have on the probability that x is forced, which is roughly p squared. So that means that we actually do get a lot of chances to guess with bias, and the conditioning doesn't matter much because the probability that x was forced is tiny. This can be made formal. Okay, in order to solve the other problem, we only guess with bias variables that appear in a in a maximal collection of disjoint clauses. So what do I mean by that? Okay, so we greedily construct a maximal collection of disjoint clauses. Okay, now every other clause has at least one variable in common with this maximal collection. Now, what we do is we only guess with bias variables that appear in one of the disjoint clauses. So this simplifies the analysis. So we specify in advance which clause would be used to bias each variable that appears in the formula. Okay, so the whole algorithm for not all equal 3-SAT is the following. So we need to take into account the fact that maybe the maximal collection of disjoint clauses is actually small. In that case, we won't have a lot of opportunities to guess with bias, but then that's easy for a different reason, because then we can simply enumerate over all variables that appear in the disjoint clauses. And what remains is a 2-SAT instance that we can solve in polynomial time. Okay, so that's roughly the details for not all equal 3-SAT. I'm guessing the minus 30 seconds that I have. What do we do with 3-SAT? So in 3-SAT, the thing is that we suppose that we actually know the weight distribution of the clauses in the maximal collection of disjoint clauses. Now there are two cases. Either this weight distribution implies some bias on one of the first two variables appearing in these clauses, then essentially the same ideas we used for not all equal 3-SAT apply. Otherwise, by a lucky coincidence or lucky occurrence, we can see that actually if there is no bias on the first two variables, then the weight distribution must be the following. That means that in almost all clauses, the number of ones is actually odd. That's almost like a linear equation, and that we can use in a different way. Okay, do I have time for the open problems, or should I stop now?
Okay, let's start to see. Are there any questions for Uri? You can write it down in the chat box, and I'll try to go over it. Okay, take a minute to conclude, maybe. And
yeah. Okay. So there are many open problems. Can we get more substantial improvements? We hope so, but we also have some lower bounds to how much we can get, at least with the current ideas, without throwing in new ideas. What we don't particularly like the use of the maximal collection of disjoint clauses. We also lose a bit in the analysis by using it. So the question is, can this be removed? Can we generalize Heracles' argument that PPSZ also works for without the uniqueness assumption to our version of the algorithm? It seems that it should be possible, but there are some subtleties that we are not able to handle yet. Okay, on a more, maybe more important, is this the right asymptotic behavior of CK? Or can this be improved? That would be, improving it would be a major problem. And also, all the upper bounds that we have, both for PPSZ and biased-PPSZ are not known to be tight. So can either the analysis or the lower bounds be improved?
okay, thank you. Thanks a lot. Uri, we have a short question from Fabrizio. We don't have much time, so maybe if you can really just briefly answer that. Can you spend a few more words about the weights?
Okay, so in half a minute.
Yeah,
so
even less.
The collection of disjoint clauses. This is a fixed collection of clauses. The algorithm builds it. Now, the Under the unique satisfying assignment, each such clause has a weight, the number of literals which are true in each such clause. Now, in principle, we don't know this distribution, but we can easily enumerate over it. So we might as well assume that we actually know W1. This is the fraction of the clauses that have only one true literal among this collection. W2 is the fraction of clauses that have two true literals, and so on.
Okay, perfect. Okay, thanks a lot, Uri.